Okay. Going to go ahead and talk through the Unit 3.9 handout. So we can try to be clear on these different topics. So we have the first items that will be on your review sheet are these ones of identifying the vibrator and the radiator, okay, for different kinds of instruments. So here for percussion, we actually have 4 different families that have different kinds of oscillators and filters and radiators. Okay. So for the membrane instruments, those would be all of the drums. There is usually some striking action that is the excitation. And then the oscillator is the membrane or the drum head. Which is a 2-dimensional surface, usually a circle, and it's fixed at the edges. So it does have a lot of resonances, but those resonances are now 2-dimensional resonances, and their frequencies are not harmonically related. They're very close together. The filter and resonator on the drum and the primary radiator are also the membranes. The body of the drum can also reinforce some sounds, but the primary resonator and radiator are the membranes. Same with the bar. Well, the bar instruments. Okay, so membranes. We're thinking all of the drums. For the bar family, we're thinking the marimba, the xylophone, and all of the other variations, the ones that have bars laid out like a keyboard. Okay, and then there's also a different type, which is like a triangle. Would be a bar instrument as well. Okay. There is a striking position. The oscillator is the bar. It determines what frequencies will be in there. There is also the bar that is a filter resonator, but it's also often these will have tubes in this first category of the marimba and xylophone. And then the radiator will also be the bar and the tubes for the marimba and xylophone family. For plate, you're thinking of cymbals and gongs, metal circular things. Okay, there is again the excitation is striking. The oscillator is the plate, the metal circular circle of this circle of metal. And then the filter resonator is the plate and the radiator is the plate. Okay. And then for the bell, that's any kind of bell, right? Bells have kind of this shape to them for an important reason. Okay. They are usually struck. There's usually a striking device inside the bell. The bell is the oscillator and the resonator and the plate. Or I'm sorry, and the radiator are all the bell. Okay. When given 5 diagrams of wave patterns on a drum head, identify which could represent the natural modes of the drums. Okay, so I'm going to draw some circles here. Okay, so pretend those are different or about the same. It doesn't really matter. Okay, so I'm going to draw the nodal lines. These are 2-dimensional surfaces now. So instead of like our waves on a string, right, we had node points. Now because that's kind of just 1-dimensional, right? Now that we're in 2 dimensions, we're going to have node lines. So for example, we could have a node line like this, or nodal lines like this. Okay. Okay. And for those kind of nodal lines, adjacent sections are out of phase. That means when the right side is up, the left side will be down. And when the left side's up, the right side will be down in this first one. And then in this more complicated one I drew here, it just means that the adjacent sections would be out of phase. So when all the pluses are up, all the minuses would be down, and the nodal lines would be the points in between that do not, the lines in between that don't move. Okay, so that's one type of mode, or of nodal lines, one type of modes. Okay, and then the others are circles, and they should be right in the middle of the other circle. Okay, maybe I'll do that again and copy it. Okay, so you can also have one that is bigger and one that is, say, smaller. Okay, those would be different kinds of modes that would have circular nodal lines. And so that means, again, that adjacent sections are out of phase. So if the inside of this was going up, the outer ring would be going down. The outer ring's going up, the inside would be going down. And here you would have plus minus plus, meaning the outer ring in the middle would be in phase, going up together, while the middle ring was down, and then they would switch back and forth. Okay. So these are radial modes with straight line nodal lines and circular modes with these circles. And then you can have ones that are mixed up, where you have a circle, but then you also have, say, a line through it. Okay. And again, adjacent sections would be out of phase with each other. Okay. But the rules are, okay, nodal lines must go from side to side through the middle. So all the way across and through the middle. And then the nodal circles, they must go all the way around and be centered on the middle. So for example, something that kind of did that would not work, okay? Because the straight lines don't go through the middle and the circle doesn't go all the way around. Or if there was, a line that was kind of like over here, it was a circle all the way around, but didn't go through, have them centered at the middle. None of those could be possible realistic nodal lines. Okay, so now we're on to this question number 1. Which of the following describe nodal lines on the membrane percussion instruments? Okay. Nodal lines must extend from one side of the membrane to the other, passing through the middle. True. Circular nodes must form a complete circle and be centered on the middle. True. And this one is false. Okay, so the correct answer would be D on that one. Now, number 2 says, why do membrane percussion instruments generate closely spaced partials? So here are the reasons. You have a 2-dimensional surface that is vibrating. Okay. Is the primary one. Okay. They do support standing waves, meaning repeating patterns, and those standing waves have natural frequencies or resonances, just like the strings in the tubes. Okay. So A is false, B is false, C is false, D is the one that is true. Okay. The modal frequencies, these natural resonance frequencies, okay, just so you know, those are all synonymous. The natural frequencies, the resonances, those equal the modal frequencies. Okay. They are closely spaced inharmonic partials. It's also false. So that means that a spectrum from a membrane instrument might look like this. Something like that, just a whole bunch of different lines. Okay, so inharmonic partials, closely spaced. Is how you would identify a list of frequencies as coming from a membrane percussion instrument. Okay, now moving on to the bars. The interesting thing with the bars is that they are not fixed at the ends. They are fixed kind of in the middle, or sorry, a distance from the ends. So I'm going to write these here so then I can try to draw them. So for example, mode 1 would be something like this. Okay, to where the ends now are antinodes because they are free ends of the bar, as is that. So that's the mode shape. This is the neutral bar, okay, of length L. So this is like the bar. Okay, with it's tied down in two places. So that would be what mode 1 would look like, where the center of the bar was out of phase with the ends of the bar, vibrating between that shape and this shape, up and down. So then mode 2 would have an extra node in between, like that. Let me just move this dot over just a spot. Okay. And then it would be oscillating between there and something like this. Okay, so again, the ends are free, so they have antinodes. So that would be mode 2. This would be mode 1. And then mode 3 would go something like this. And then the alternating. Now, important thing here is to remember, as we talked about with the strings before, if the excitation, which in this case is the striking, occurs at a node of one of the modes, one or more of the modes, those modes are not excited, not given any energy, if you wish, by the striking, and will be absent from the spectrum. Okay. So now if I label a couple of points on here, I'm going to put in some green dots, green lines. These are just to mark the same position on each of these bars. They're not evenly spaced. They're just representing different points. So we'll just call them A, B, C, D, E, F, G. 7 different locations on the bars. Okay. What this means is if the bar, okay, and it actually can't be struck at B or F because that's where it's tied down. You could, but no modes would sound because they all have nodes there. Okay. If the bar is struck at point D, okay, so this point D right here, the even modes 2, 4, 6, 8, will not appear in the spectrum. Sorry. The even modes are not excited, and their frequencies won't appear in the spectrum. That's the thing. Whereas if it was struck at point C or E, say here or here, then mode 3 would not, because mode 3 has nodes there, but mode 1 and 2 do not. Another thing about these bars is about the partials. These have a few, the spectrum from these sounds will show from bars. They will have a few widely spaced partials. They're not harmonic because of the thickness of the bar. Undercutting is used to try to make them a little bit more closely to being harmonic. But they do have a tone or a definite pitch. Whereas these inharmonic partials for the membrane that are closely spaced result in an indefinite pitch. Okay, so real quick about the bells. Okay. The bell family. So bells have this special shape that is a bell. Okay. That shape, okay, this is again a two-dimensional surface. And there are standing waves, natural, which is synonymous with natural mode, that have specific modal frequencies, which is synonymous with natural frequencies, which is synonymous with, or which are also resonances. But the frequency ratio, because of this very specific shape a bell has, so the frequency ratios of the mode frequencies, the FN, okay, for the mode 1, we'll just call that F1. Mode 2 then would be F2. Let me just make sure I've got right relationship here. It's the bottom is the hum, and then you have the octave, and then you have basically the one above that, and then the next octave. So you have one of them that is not in harmonic representation of the other. But let me just get, there we go. Okay. Okay, so I will write it out more official. This is also in the handouts. Okay, you have the hum frequency, which is the lowest frequency mode, and that is an octave lower than the pitch. Pitch is called F prime. That is the perceived pitch. That hum mode doesn't resonate or vibrate or radiate well. So at the prime is the perceived pitch. Then there is the next one up is a minor third above. Above the perceived pitch. And then you have the fifth, which is a perfect fifth above F prime. And then you have the octave, which is an octave above. Okay. So okay, so if you want to write it in terms of F1, that would be F1, 2 F1, 3 F1, 4 F1. Okay, and then this is the extra in harmonic partial. And that's why even in choir and stuff, if you ever sing a chord with a minor third in it, it has a bell-like quality. So that means the spectrum would look something like, let me separate those a little more. So the hum doesn't sound very much, and then you have the prime, and then you have a third above the prime, somewhere in here, and then you have the fifth and the octave. So you have this one extra in harmonic partial for a bell, and that's what makes it sound like a bell. And that has to do again with the modal structure, the modes, the natural resonances of the bell shape. Okay. Bells do have definite pitch as well. Okay. So with regards to the definite pitch, bars, except the triangle, have definite pitch, and bells have definite pitch. Membranes don't have a different pitch except for the timpani, which is that bowl that kind of emphasizes certain resonances. It's not that the membrane doesn't have inharmonic partials, but the bowl emphasizes certain ones to make it have more of a pitch. Okay, so here are some examples. We're going to do this middle one, number 5, for what you might expect. These are not exact numbers, but give you the idea. For a membrane, characteristics, closely spaced, inharmonic partials. All right. Something perhaps like, we'll just start them all at 100 just for fun. Something like that, closely spaced inharmonic partials. For the bar instruments, they are widely spaced inharmonic partials. Now, you're not memorizing this exact list of numbers. You're just memorizing the characteristics Oh, and I sincerely hope there wasn't a gray box in front of this. Hold on. If there was a gray box, you have to let me know so I can redo the recording. Okay, so an example of that might be something like 100, 237, 486, something like that. And typically there's just a few of them. Make that different. Okay. Then for the bell, the partials, the natural frequencies are harmonic except for one. So something like 100, 200, 238, 300, and 400 hertz. So integer multiples except for the middle one, the third one. Piano can be described as having slightly inharmonic partials. Something like 100, 203, 305, 408, etc. Whereas the violin, our fixed string model with harmonic partials, is a very good approximation for the bowed string family because their strings are not yet so stiff. They would have harmonic partials. So the corresponding list would be 100, 200, 300, 400, etc. So you don't have to know these exact numbers. What you need to understand are the words that I wrote and how those words relate to any set of numbers. Okay, whether they're harmonic or inharmonic, closely spaced in frequency, or widely spaced in frequency. Okay. And just to clarify here, triangles are indefinite pitch instruments. And timpani, the bowls, are filters that emphasize some of the inharmonic partials. In a way that gives a perception of a pitch, or at least, different ranges, but it's the filter of the timpani, the bowl acting as a filter that does that. Okay, now this is lots of different categories, but hopefully that will be useful for you. Thank you.